Well, thank you for inviting me to this workshop. Today from JPL, I'm going to talk about words making a millimeter wave band carbon wave parametric amplifier based on kinetic inductance. Okay, I'll just quickly describe how we started working on this type of device. My group at JPL does a lot of work on superconducting detectors for astronomy instruments. And one detector that we've been working on for several years is the microwave kinetic inductance detector. And so this is essentially a photosensitive thin film microresonator where incoming photons break Cooper pairs in a superconductor. They change the kinetic inductance, and then you read that out as a frequency shift. And what we were trying to understand is how large the drive power we could use to read out the frequency shift, because that determines the noise of the device. So we found that when we are increasing the drive power, our resonance starts to shift to lower frequencies, and then it bifurcates, and the behavior becomes hysteretic, with the more striking behavior coming from the downward sweeping resonance curves. So here we're shifting the resonance frequency by many times the natural line width. This can all be described using a nonlinear Duffing type resonator model, where the kinetic inductance is current dependence. It has a I squared nonlinear term. And that's all been understood for quite some time. What was new in these measurements and not seen before in previous studies is that there was no connected nonlinear dissipative response of the resonator when we drove it into this nonlinear state. And so that now this effect becomes interesting for device applications similar to what you can do with a Josephson junction, which is another example of a purely reactive nonlinear element. Okay, and so this effect also occurs in transmission lines. And so here we're injecting a DC current through a transmission line, which is a niobium titanium nitride microstrip line in this case. The transmission line has a periodic structure in it, which creates a band gap. You can see in the upper right. And we're just using that here in order to monitor the response of the film to the DC current. So we're measuring the shift of the band gap frequency as we increase the current, and that tells us the change in the propagation velocity on the transmission line. And from that, we can derive the change in the inductance of the line. And so here we're seeing a pretty large nonlinear shift of about 20%. And this transmission line has a physical length of about 21 millimeters. It's a very slow wave structure. I'll talk more about the actual structure of it in a minute. But the propagation velocity on the line is about 1% of the speed of light. And so that corresponds to a electrical length of, should be 2.1 meters. And so at the measurement frequency of 38 gigahertz, we're getting about 167 radians of phase shift, and we're not seeing any measurable change in the loss in the transmission through the device. And so this is actually a useful device in itself. It could be used as a current programmable millimeter wave delay element, and we've been looking at using this as an on-chip Fourier transform spectrometer for astronomy type observations. The propagation velocity on the line also responds to an AC current, also as I squared. And so the superconducting transmission line is analogous to a Kerr medium. And so optical medium with a third order nonlinear susceptibility, where the optical index varies as the intensity of a wave. And so it supports all the normal four-wave mixing nonlinear optical processes, such as parametric amplification, which is basically the stimulated conversion of two pump photons into an additional signal photon and an idler photon, or third harmonic generation, or frequency conversion versus four-wave mixing. And so we can now make devices which are analogs of nonlinear optical devices, circuit analogs operating in the frequency range of gigahertz to terahertz. The upper frequency limit is set by the gap parameter of the gap frequency of the superconductor, which is a frequency beyond which photons break Cooper pairs in the superconductor. And so for one of our favorite superconductors, niobium titanium nitride, that's about 1.4 terahertz. Let's see. Oh, so I just wanted to mention that these nonlinear transmission lines are actually very versatile nonlinear media. So we can also use them as three-wave mixing nonlinear media by injecting a DC current through them, in addition to the other tones that we put through. So this DC current then breaks the symmetry, and it gives you a nonlinear term in the inductance, which just varies in proportional to the current. And so this is like a optical medium with a second order susceptibility. And it supports the various three-wave mixing versions of the nonlinear optical processes. Okay, so I'll just talk about an implementation of this type of device at microwave frequencies, because it's basically just directly transferable to the millimeter wave band. This is the kinetic inductance traveling wave parametric amplifier. And this is based on a niobium titanium nitride microstrip line. Our microstrip has an inverted structure. So the microstrip conductor is on the bottom, and then there's a sky plane on top of it. And the dielectric in the microstrip is amorphous silicon, which has a loss tangent of about 10 to the minus 5. The structure that we use is shown below on the right. It's a thin conductor, or narrow conductor, to enhance the nonlinear effect. But then it has a series of stub sections periodically attached to it. And one purpose of these sections is to decrease the characteristic impedance by adding some capacitance to this line. Otherwise, the narrow microstrip line would have a characteristic impedance of a couple of hundred ohms. So this device has a total length of 10 centimeters. The line width is 0.32 microns, and the propagation velocity is a bit less than 1% of the speed of light, similar to the other one. So this is by applying a strong pump tone, produces gain via four-wave mixing. And the gain curve is shown here on the left. It's divided into three sections. I've labeled two of them arbitrarily, signal and idler band. When you put a signal into the lower frequency signal band, it is amplified and it also generates an output tone at the in the idler band. The center plot just shows that this the bandwidth over which this device amplifies can be tuned quite a bit by adjusting the frequency of the pump. And the device is near quantum limited, shown on the right. The behavior of the device can be understood quite well using just the coupled mode theory from optics. That's shown as the model of the device behavior is the dashed red line here, and it agrees quite well with the measured gain. The key to making this work is to properly engineer the dispersion of the transmission line. And so there are two main goals there. First, we want to phase match the process nonlinear process that we want, parametric amplification in this case. When I say phase match, we need to try to maintain a certain phase relation between the different tones, pump signal and idler tone, as they propagate down the transmission line. And that requires a certain relationship between the propagation constant at the frequency of those different tones. The second goal is that we need to mismatch all of the other nonlinear processes that you can possibly get. So as a bit different than for at what happens at optical frequencies. There the materials have a strong inherent dispersion, and it's difficult to just match one process. But the superconducting transmission line, at least well below the gap frequency, is virtually dispersionless, meaning that you can end up matching to a number of these different processes, and then you end up with a cacophony of tones, and the device doesn't work very well. So in our structures, we have two knobs that we use to do this dispersion engineering. First thing we do is we introduce a periodic modulation in the length of the shunt stub sections, and that opens up a band gap in the transmission. And then we put the pump near the band gap frequency, where you end up with seeing some dispersion near the edges of the band gap. And the point here is to try to slow down the pump tone a little bit in order to compensate for the nonlinear dispersive effects, which are the self and cross phase modulation, which would otherwise, even in a uniform transmission line, it would otherwise give you a phase mismatch. And then the second goal of mismatching the other processes is done by adjusting the overall length of the stubs, and that can be done while maintaining 50 ohms by adjusting the spacing between them. And so these stubs, because they have a certain length, introduce dispersion at high frequencies, which you can use to then mismatch the processes that you don't want. Okay, so that was a lot about our microwave version of the device. But all of this can be translated in a straightforward way to millimeter band. We can calculate what we expect behavior to be at millimeter wave frequencies by calculating the complex conductivity using Mattis-Bardeen equations. And an example is shown here for a niobium titanium nitride microstrip, which has a width of 1 micron in this case. This is a suitable geometry for a millimeter wave TWP. What we find is that, well, plotted on the left is attenuation versus frequency, and I've plotted it in dB per wavelength at different temperatures. And it's in dB per wavelength because we need a certain amount of wavelength to make our paraamp work. It's around 200, say. And so this shows that you can run the device at about 3 Kelvin, 2 or 3 Kelvin, and still have minimal loss all the way through the millimeter wave band. The frequency dependence of the complex conductivity also adds some dispersion at high frequency as you approach the gap frequency. So the transmission line is no longer completely dispersionless, and this will end up limiting the bandwidth that we can get for our amplifiers. All right, so we made a test setup in order to test our these amplifiers. We're targeting demonstrating this at W band, so approximately 70 to 110 gigahertz. And this test setup is based on a GM cooler, which pre-cools a helium-4 absorption fridge with a base temperature of 0.9 Kelvin, which is cold enough for what we want to do. 1 photon at 100 gigahertz corresponds to about 5 Kelvin. The cryostat has 4 WR10 waveguides going in. Some of the thermal breaks are made with short stainless steel sections. And then there are also these thermal isolators, which are based on waveguide flanges that are just held close to each other, but one has a photonic band gap structure machined in it to prevent leakage of the power out. And then we have just commercial LNA and isolators. And for noise measurement, we have this variable temperature waveguide calibration load that was described in a paper by Jacob Cui a few years ago. So we're using waveguide because at these frequencies, the coax just becomes much too lossy. And so the idea is to insert our paraamp chip into a waveguide split block shown here. And then the power is coupled from the waveguides onto our microstrip line using what are called waveguide probes, one on the input and one on the output. These probes act like antennas. And how to make these probes is pretty well understood. There's a famous paper also by Jacob Cui some time ago showing how to do this. And it turns out you can do quite well as far as the return loss over the entire W band. Here we're at S11 of about minus 20 dB. You have to do pretty well for this to work for a paraamp because TWPs basically don't like reflections. They end up turning into oscillators if reflections are too great. For the work that we've been doing, we've kind of changed the traditional design a bit, and we're using this inverted design where we place the device side of the silicon chip in the channel between the waveguides face down in order to try to make a better ground connection. But it's also possible to do that with using more standard techniques. This is showing that you can machine or pattern the ground plane into a RF choke structure in order to present a good RF ground at the waveguide wall. The chips need to be quite thin for this to work in order to avoid perturbing the waveguide too much. And so we're making these on 100 micron silicon for now. It turns out to be good enough for W band. The way that we're making these devices on thin chips is using what we call a SOE process, which is borrowed from work on mixers. So we use a silicon on insulator wafer, which has a thin layer of crystalline silicon on a silicon dioxide layer on top of a thicker handle wafer. And we fabricate our devices on the top device layer, and we etch through the top silicon layer in order to define our chips, and we wax that down to a carrier wafer. We etch away the handle wafer and the box, the silicon dioxide layer, and then we dissolve the wax to release our chips. We make these chips so that they're still attached at that point to a silicon frame so that they don't all just float away. And then we can break them out of the frame. They're connected. Photograph isn't very good, I guess, but there are small breakaway tabs holding the chips at that point. All right, and so this is a picture of one of our TWPs for W band. The chip dimensions are shown there. This is what we call a narrow band design of the W band TWPA, and so we use the short versions of the microwave of the shunt stubs in this case to provide some dispersion in order to limit the bandwidth over which we're getting gain to the W band. And the issue here is that the TWPA is naturally very broadband, and if you have gain, say, at below the cutoff frequency of the waveguide, then you end up making an oscillator again. So on the top right is the transmission that we measured through this particular device. And you see it, there was some extra loss in this device, but you can see the band gap that we designed in. And then applying the pump, we measure the gain shown below. This is pump off versus pump on versus pump off gain. So the actual gain, for the actual gain, you'll have to subtract the about 8 dB of loss that we had in that case. The loss for this device, we think, was coming from an error that we made in the housing. We had not machined an air channel below where the device sits in that case, and we think that the fields from the transmission line were seeing the copper housing. But you could ask, maybe it's due to dielectric loss, which I haven't talked about yet at millimeter wave frequencies. We've investigated that by making microstrip resonator devices, these small hairpin resonators, and we've measured them. The limiting loss is clearly the two-level systems loss from the dielectric, from the characteristic power dependence that we see. And but fitting the data, we get a Q of about 23,000 in this case, which is would produce minimal loss through our amplifier. You can compare this value to the what we measure at microwave frequencies, which is and so it's a bit lower in this case for some reason. We're not quite sure why that is. And you may expect some frequency dependence, but according to theory, the loss should be not very frequency dependent, at least. Okay, but so now we fixed the problem with our device, our housings, and the results are shown here. So these are transmission plots comparing our TWP. You can see where the band gap, design band gap is, to just a section of waveguide, and so there's at least the lower half of the W band. You see very little difference between the two. On the bottom, it shows where we are with the gain measurements for this device. We're getting a few dB gain, so it's not working quite yet, but we think this may be limited by the fact that the gain is over too wide a band still, and so we're getting reflections at a certain pump power. Okay, so you can think about what's possible at higher frequencies yet, or in terms of widening the bandwidth of this design more. And so I mentioned that the device we'd measured so far was purposely made narrowband in order to fit both the signal and idler bands in the single mode bandwidth of WR10. But you can, if we remove the shunt stubs now, and just rely on the kinetic inductance, the frequency dependence of the kinetic inductance in order to mismatch the higher frequency processes, then you can make a much wider band design, and that's shown as the dark blue curve here. So here we have an amplifier that can amplify in just a signal band over the whole bandwidth corresponding to W band. And then the idler band appears at higher frequency. And we can go higher up in frequency yet, but you can see that the bandwidth starts to narrow, and this is due to the frequency dependence, again, of the complex conductivity. And so, but if we're operating in waveguide, we have to do something in order to protect against these oscillations that you would get with gain outside of the waveguide bandwidth. And so here, the idea will be to make on-chip diplexer or triplexer circuits. And basically, the idea is that the pair amp should see only a matched load over a very wide frequency band. And then we use contiguous band triplexers to send frequencies outside of the WR10 bandwidth to just terminations. And on the left is a simulation of, this is just a diplexer circuit designed for wideband match in order, and just to show that this should be possible. We've also have quite a bit of experience actually making filters like this at millimeter wave frequencies, and done in the astronomical focal planes that we make. So this just shows an example of types of circuits that we've made. On the left is a wideband antenna, and then working between maybe 100 and 400 gigahertz. And then we take the power from that antenna and we split it into 4 different bands using these filters in order to send the outputs of those to separate detectors. And that's used to make a multi-color focal plane. All right, and then another type of device that we've been playing with is a traveling wave multiplier. And so here, what we've done is we've demonstrated a multiplier between about 33 and 100 gigahertz, and showed that we could get reasonably high efficiency out of it. This is another device with applications to astronomy instruments. It's useful to have efficient multipliers at high frequency. But this, a similar device could also potentially be used as an up converter. So you could up convert potentially microwave to millimeter wave signals coherently. Right, so that takes me to the end. So what we've done is we've demonstrated a niobium titanium nitride microstrip geometry, which basically is a analog of nonlinear optical devices. We've shown that we can make, we've demonstrated that we can get wideband 4-wave mixing at W-band frequencies. Device is not working, and it's not in a usable state yet, but it seems to be close. And so we think that quantum limited amplifiers through the millimeter wave band should be coming pretty soon. There are some engineering challenges left. All right, thank you for listening. Yep. Oh, sorry.
So when you show the gain spectrum, it looks a little bit jagged. Is that a real feature? Oh, sorry. Is that a real feature of the device, or is it just because of measurement?
Yeah, no, it is a real feature of the device. And so with these types, these are, yes, they're ripples in the gain. And so the challenge with these traveling wave amplifiers is always to reduce reflections. If you have and you can have fairly small reflections, but if you have a gain medium in between them, then you end up, the ripples end up growing.
Also a quick question. So what's the typical RF power you have there to get the 20 or 30 dB gain?
Yes, for this device, it's around 10 microwatts.
Hey, how do you calibrate these measurements?
We calibrate them.
Yes.
So for gain measurements, well, I mean, we just replace the TWP with a through transmission line. Sometimes we, at lower frequencies, we have switches that work, and so we can, like a transfer switch arrangement. These are cryogenic switches. Well, as far as vortices go, the line widths we're working with are much narrower than the Pearl length in the film, and so we don't expect to get vortices in the conductor at least. You can worry about getting them in the ground plane. You can do things like putting in perforations if that is a worry. But yes, when you apply a current, and especially with these high kinetic inductance materials, Mattis-Bardeen is not going to be precisely right. You have a smearing of the gap, and so it's a slightly more complicated calculation, which can be done. In the regime that we're working with here, that's not a very large effect, but as you get closer to the gap frequency, then you will start to see some deviations. Yeah, it's not very high for our films. It's around 6 or 7 picohenries per square.
Yeah, I had a question for you and maybe also even for Michelle. But so I was just trying to understand. So right, these Josephson junctions, the conventional kind, are great and they work pretty well. These kinetic inductance devices also have a very clean nonlinearity, it seems like, and I'm just trying to. I wonder, is there like a figure of merit or something that we could compare these two nonlinearities? Like, if we wanted to say, oh, an aluminum tunnel junction is better, or I mean, obviously it depends on what you're doing for lots of practical reasons. But is there a way of saying which nonlinearity is I don't know, cleaner or stronger in some?
Yes, there are a number of ways you could compare them. Certainly, the kinetic inductance nonlinearity is not as large as you can get with the Josephson junctions, but then I think probably in practical cases the loss in our paramps is less than in a Josephson TWP because of the complex fabrication, the more complex fabrication. And so if you measure, I think, the loss through a Josephson TWP, at least the ones that are sort of available now, you'll get several dB of loss with the pump off already, right? That's what I'm told by people that use them. And in our case, that loss can be quite small. And so, that you can try to overcome the loss with and in some ways, having loss kind of stabilizes the gain a bit because, the loss applies to the reflected power as well. But then if you are interested in doing things like squeezing stuff, it'll be a problem. There are many other ways to compare the two devices, I guess. I think we're sort of using our devices in many cases for sort of practical amplifiers where you can amplify stronger tones than you can with Josephson TWPs, for example.
Yes, I can offer an answer to the question, Dave. So Peter has shown that there's a nonlinearity. When you showed the fourth order nonlinearity, you had a term that was square in the current, but this you had at the denominator a current which you could interpret as a sort of critical current. And so you can compare this critical current in this formula for the from what you would compute from the sort of plasma frequency of the film, which is an intensive parameter, and the also the characteristic impedance, and you can see if by how much those critical current differ, and that would give you a sort of intrinsic strength of the nonlinearity that you could compare with the dissipation. So that maps this kind of film with an array of Josephson junctions.